Welcome back to the Deep Dive. Today, we're tackling something huge by starting incredibly small. We've got this amazing set of sources on atoms, materials, even massive engineering projects. And the big question we're asking is, how does figuring out these tiniest particles, atoms, let us build the biggest things, think skyscrapers or, even getting to space?
It's a fascinating scale-up, isn't it? We're essentially going from seeing individual atoms harnessing subatomic particles all the way up to, well, advanced materials and why some structures work and others just can't yet.
Okay, let's unpack this. Let's start at the beginning. The word atom itself, right? Greek for indivisible. John Dalton proposed that, but scientists, well, they pretty quickly found out that wasn't quite right.
Exactly. That realization was huge. Dalton gave us a foundation, definitely, but atoms weren't solid balls. They have parts, protons, neutrons in the middle, this dense nucleus, and then electrons buzzing around. Mostly empty space, actually.
But full of energy.
Immense energy. But first, how do you even study something that small? We're talking nanometers, a billionth of a meter. Like microscopes they don't work. Atoms are smaller than the wavelengths of visible light.
Right. So you can't bounce light off them to see them. So how do they do it?
Well, they had to think differently. Step into the quantum world. That led to the scanning tunneling microscope, the STM, forget light. This uses an incredibly sharp probe. I mean, the tip can be just 1 or 2 atoms wide.
One atom. Wow. And it gets super close to the surface.
Unbelievably close. Closer than a hair's width, but there's still a gap.
Okay, so if there's a gap, how does it make an image? What's crossing that space?
That's the weird part. It's called quantum tunneling. Electrons behaving like waves have this probability, this chance of just jumping across that tiny gap, even though classically they shouldn't be able to.
They tunnel through.
Sort of, yeah. They appear on the other side, creating a tiny electrical current. The STM keeps that current constant by adjusting the probe's height, and by mapping those adjustments, it builds up a picture of the surface, atom by atom.
Incredible. That's how they could eventually, arrange individual atoms, right? To spell things out.
Precisely. It showed this ultimate control over matter, down to the single atom.
And that control extends to the energy inside the atom,
Right.
the nucleus. Our sources bring up Einstein, of course, E equals mc squared.
Right. And the key there is the c squared. Speed of light squared, it's a massive number. So converting even a tiny, tiny bit of mass, like less than 0.1% during nuclear fission, when a nucleus splits, releases a huge amount of energy.
We saw the destructive power first, obviously, in World War II.
A terrifying application, yes. But the controlled version powers nuclear reactors today. What's fascinating here is how understanding these particles led to other things, too.
Like megal uses?
Exactly. Particle beams, protons, neutrons, they started as tools to smash atoms, figure out what's inside.
Yeah.
But now, doctors use them for cancer therapy. They can tune the beam's energy so precisely.
So it hits the tumor.
Right. It deposits most of its energy right in the tumor, damaging it, while doing much less damage to the healthy tissue around it. It's a massive improvement over older radiation methods.
Okay, let's scale up a bit. From single atoms to molecules. And let's talk about a really common one, water, H-zeros. We learn about strong bonds, like covalent bonds, where atoms share electrons. But water's special tricks seem to come from weaker forces.
That's right, hydrogen bonds, they're key. In water, the oxygen atom pulls the shared electrons a bit more strongly than the hydrogen atoms do. This makes the molecule polar.
Meaning it has slightly charged ends, like tiny magnets.
Exactly like tiny magnets, a slightly negative end near the oxygen, slightly positive near the hydrogens, and these charged ends attract the oppositely charged ends of neighboring water molecules. That's the hydrogen bond.
And that's why water is so sticky.
Sticky is a good way to put it. Compared to similar molecules like hydrogen sulfide H-rose, which is a gas at room temp, water molecules cling together much more tightly because of all these hydrogen bonds.
Which explains why it takes so much energy to boil water, right? You have to break all those extra bonds, and why it's liquid over such a huge temperature range.
Absolutely. 32 to 212 Fahrenheit or 0 to 100 Celsius. That wide liquid range is critical for life. And these bonds do amazing things. Think about giant redwood trees. How does water get 330 feet up to the top leaves?
It's pulled up somehow.
It is capillary action. The water molecules stick to the sides of the narrow tubes in the wood, that's adhesion, because the wood surface is also polar, and they also stick to each other, cohesion. So they essentially pull each other up in a long chain.
Wow. All down to those little hydrogen bonds. And what about water freezing? It does something weird there too, doesn't it? It expands.
It does. Almost everything else contracts when it freezes, gets denser. Water molecules arrange themselves into this open hexagonal crystal structure when they form ice. takes up more space.
So ice is less dense than liquid water.
Which is why it floats, and thank goodness it does. If ice sank, lakes and ponds would freeze solid from the bottom up in winter. Aquatic life couldn't survive. Instead, the ice forms an insulating layer on top.
A tiny molecular detail with massive ecological consequences. Okay, let's pivot to engineering. Our sources really hammer this point. Technology is often just limited by the materials we have.
Oh, definitely. The jet engine is the classic case. People understood the basic idea, continuous combustion, thrust for a while. Think squids, right. But making it work was impossible.
Why? The heat?
The heat, exactly. Inside a jet turbine, it can hit, 4,500 degrees Fahrenheit? Materials just melted or failed. The whole jet age basically had to wait for the invention of superalloys.
Nickel and cobalt mixtures, mostly.
Yeah, materials finally tough enough to handle those temperatures without failing.
And that search for better materials led us into the age of polymers, too. Plastics.
Right. Long chains of molecules, usually based on carbon. Suddenly, we had materials that were lightweight, didn't shatter like ceramics, and didn't rust or corrode easily like metals. Super useful.
But there's a downside. That durability is now a huge problem.
A massive environmental problem. Those strong chemical bonds and long chains mean things like plastic bags or bottles stick around for decades, centuries, maybe even longer. They just don't break down easily.
Yet that same polymer science gave us some incredibly strong materials, too. Kevlar comes to mind.
Ah, Kevlar. Amazing stuff. A type of polymer, yes, a polyaromatic amide. Weight for weight, it's nearly 5 times stronger than steel.
5 times?
Yeah.
How? What makes it so strong?
Here's where it gets really interesting. It's all about the structure, how those long polymer chains are arranged. In Kevlar, they're highly ordered, lined up almost perfectly parallel, like uncooked spaghetti.
Okay, so they're lined up.
And because they're lined up so neatly, they can form tons of those hydrogen bonds, the same sticky force we saw in water between the chains. This locks the whole structure together incredibly tightly. It creates this dense, crystalline structure internally.
So when something like a bullet hits Kevlar,
it has to break not just the chains, but also overcome all those hydrogen bonds, holding the chains together side by side. The material absorbs the energy that way. That's how a seemingly soft vest can stop a bullet.
incredible. And we don't always use these materials pure, right? We mix them. Composites.
Exactly. We embed strong fibers like Kevlar or even stronger carbon fibers into a matrix material, often a plastic or sometimes a metal. You get the strength of the fibers combined with other properties from the matrix.
And this solves other problems, like metal fatigue.
Big time. Metal fatigue is nasty. Metal can weaken and break over time just from repeated stress. Even if the stress isn't that high each time, it's often invisible until it fails catastrophically.
Like those early jetliner crashes. The de Havilland comets.
Precisely. Stress concentrated around their square windows, cycles of pressurization, snap. Composites don't really suffer from fatigue in the same way.
Which is why modern planes use them so much.
Absolutely. The Boeing 787 Dreamliner, for instance, is about 50% composite materials by weight, strong, light, and resistant to fatigue. It's also used in things like high-performance prosthetic limbs.
Okay, this brings us to the ultimate challenge, maybe. Building really, really tall structures, getting off the planet without rockets.
Ah, the big one. Historically, building height was limited by weight. Stone and brick are strong in compression, but heavy. Philadelphia City Hall needed walls 22 feet thick at the base just to hold itself up.
Then came steel, and reinforced concrete steel handling the tension, concrete the compression. That gave us skyscrapers.
Right, like the Sears Tower, Willis Tower now. But even those materials have limits when you start thinking really big, like space big.
You mean the space elevator concept?
Exactly. This idea of a cable stretching from Earth's surface way up into space, maybe 62,000 miles or 100,000 kilometers, climbers could just ride up it, much cheaper than blasting off with rockets.
But the physics are nuts. To keep it taut, the center of mass has to be way out at geostationary orbit.
About 22,300 miles up, yeah. So it orbits at the same speed Earth spins, and you need a counterweight even further out. The cable has to support its own enormous weight over that distance.
And current materials, they just can't.
Not even close. Steel, Kevlar, they'd snap under their own weight long before reaching that height. The tensile strength needed is astronomical.
So what could possibly work?
Right now, the only material we can even conceive of is based on nanotechnology. Carbon nanotubes.
Rolled up sheets of carbon atoms.
Essentially, yes. Perfect cylinders of carbon atoms. Theoretically, their tensile strength could be more than 100 times that of steel, and they're incredibly lightweight.
So we've gone full circle. To build this massive structure reaching into space,
Hmm.
we need perfect control right back down at the level of individual carbon atom.
Exactly. That's the connection. So what does this all mean?
Well, it seems like every major technological leap, from tiny microchips made using techniques like STM, to life-saving medical treatments with particle beams, to bulletproof vests, maybe even one day a space elevator. It all comes back to understanding and manipulating matter at the atomic level.
That's the thread connecting everything. Our ability to engineer materials fundamentally dictates what we can achieve.
And looking ahead, the sources hinted that we're moving beyond just strong, passive materials.
That's right. The future seems to be in dynamic or smart materials, things that don't just withstand forces but adapt to them, like those experimental active aeroelastic wings mentioned, wings that can physically change shape during flight to optimize performance or reduce stress. Materials that react.
That leads to this final kind of wild thought from the sources. They mentioned research into self-healing spacecraft skin made from a type of glassy metal.
Yes, amorphous metals. Unlike regular metals with orderly crystal structures, these are disordered, more like glass. The idea is if micrometeorite punctures the hull, the material could sort of flow just slightly and seal the hole itself. Think about materials like liquid metal alloys, which have that non-crystalline structure.
So the final thought for you, our listener, to maybe kick around, if we can make materials that heal themselves, drawing on these properties of glassy amorphous structures, how could that change things back here on Earth? Architecture, cars. What happens when the things we build can fix themselves? That's something to explore.